Every year, the processes of heading, gutting, and filleting of aquaculture species generate thousands of tons of byproducts that must be properly managed to avoid serious environmental pollution problems. In Europe, the skins, heads, viscera, skeleton, and frames are mostly used as substrates for the production of fish meal and fish oil. During decades, and still today for some farmed fish species, fish meal is the basis of aquaculture feeds. It is ideal to supply this need for fish meal and fish oil through circular economy methods. However, the current methods are less than ideal. Typically, fish meal is obtained after the grinding, separation, and thermal drying of fish discards, which is used to coagulate the protein and separate the oil. The product is profitable, although there are several disadvantages. Firstly, the wastes must be transported from farms to meal plants. Secondly, this process generally produces a low-quality product. Thirdly, the environmental impacts of those plants is in most cases huge. In the GAIN project, researchers from the IIM-CSIC have developed a very interesting alternative to bring more value to the heads, trimmings, frames, and viscera of farmed turbot, salmon, and rainbow trout. Through their innovations, they are able to produce FPH. FPH are defined as those materials rich in proteins, peptides, and free amino acids obtained from the total or partial hydrolysis of whole fish or fish waste using chemicals or enzymes as proteolytic agents. In the present approach, FPH were obtained by the hydrolysis and digestion of fish parts using a commercial protease. This process of hydrolysis, combined with steps of filtration and centrifugation, recovered clean bones and fish oils, products of potential application in human bone regeneration and animal feeds, respectively. This procedure was successfully validated at a pilot plant scale, using novel technologies to reduce time and energy required for the final drying step, which is performed by spray or freeze drying. All the steps developed for the production of hydrolysates from farmed fish are well known in the field of chemical engineering, and the operation units are easily scalable and flexible to be included in a mobile platform to process in situ on the place of waste generation, avoiding its transportation. The profitability of fish meal production is usually directly proportional to the size of the meal plant. In terms of composition, aquaculture FPH showed remarkable levels of total and soluble proteins and low amounts of moisture, oils, and ash. The protein fraction was mainly composed of peptides of medium-low sizes, well within the threshold recommended by aquaculture feed producers. This is one of the most valuable characteristics of FPH production. We can control the chemical properties of the hydrolysates by modifying the conditions of the enzyme hydrolysis and/or the downstream steps, and so to generate tailored hydrolysates for following stakeholders' requirements. Additionally, the content in essential amino acids was relevant, as well as the bioactivity evaluated. Taking into consideration these outcomes, we believe aquaculture hydrolysates can be effective ingredients as substitutes of fish meal for nutritious feeds designed for the growth of farmed fish.